mechanics, basically. So it was one of the first ideas. Good old Newton. His first law, which I'm sure you're very familiar with, there it is in its Latin, of course. Anyone here do Latin? You'd be able to interpret that for us? All right, well, for those who don't do Latin, it's basically saying this. Everybody continues in its state of rest or of uniform motion in a right line unless it's compelled to change that state by forces impressed upon it. What the heck does that mean? Basically, it simply says, well, if you're travelling, you're going to keep travelling unless some force comes along and stops you or speeds you up or something like that. You'll basically just stay in the same state. That's all it's really saying. Law 2 is the very famous one, mutationem motus proportionum. Basically, it's this. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. Motive force is proportional to change in motion. That's what it's saying. Well, that means force is proportional to acceleration. Change in motion would be acceleration, which means it must be some constant times acceleration, and that constant, very conveniently, is mass. And we get that famous equation, force equals mass times acceleration. That's our second law. Which brings us to the third law, actione contrarium. Often misquoted, but this is what it actually is. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed in contrary parts. Basically it's saying forces balance. That's all it's really saying. Now those ideas are what we use. Alright? Forces, it all starts with forces. Forces are vectors. So all that work we've done on vectors is going to come in handy. We just think of them, forces, as vectors. Any force that is not vertical or horizontal, we'll resolve it into those components and we'll keep it simple. Because that way we're just dealing with straight line motion. Just moving along the x-axis or moving along the y-axis. That's all we have to worry about. The actual force will end up being the hypotenuse of a right angle triangle formed by those two components, exactly as we saw with vectors. Resultant vectors. A resultant vector, remember, is the sum of all the component vectors. So it's the same with forces. A resultant force will be the sum of all the component forces. Here's a simple little example. We want to find the magnitude and direction of the resultant force acting on this little particle here. And we've got two forces at different angles. One's 3 newtons and one's 5 newtons. But, as I say, all they really are vectors. So if I've got that situation, and it's the sum of all the forces, well then I'll add them together. There's one vector. The beautiful thing about vectors, we can slide and move them. So I'll put the other one there, the tail on the head, and so the resultant one would be joining that up. And that's what we've got to find. Okay, well there's the diagram. A bit of geometry I could work out, that's 135 degrees. I want to find that angle there, because then that will tell me the angle that the force is going off. And we normally measure it to the positive horizontal. Okay, sine rule, and we end up with around about 28.41 degrees. So the direction, therefore, I'm saying is going off at 32.59 to the horizontal. Then I can use the cosine rule to find the size of that vector. And we end up with 7.43. So there's the magnitude and the direction. Okay, you could do it that way. But it's easier, I think, by using components. So we break those forces into components. So that 3 Newton force, I could think of as a vertical force and then a horizontal force. I just got to find one of the angles, bit of geometry again. I can, by alternate angles, that must be 60 degrees. And I can do the same for the 5 Newton force, and that angle in there, well, we already know that angle is 15 degrees. So there's my object. Vertically, I now have 3 sine 60. It's opposite the 60 degrees, so it must be sine. So we end up with 3 sine 60. I also have 5 sine 15 going vertically. Horizontally, I'll have 3 cos 60 and 5 cos 15. Pulling those components together, there's my resultant force. Now, I've approximated, of course, there. So 6.3296 in the horizontal direction, 3.8922 in the vertical direction. But then it's just a vector. So I know I'm going horizontally and vertically. It's now a right-angled triangle, heck of a lot easier than having to use sine rule and cosine rule. So the magnitude is just the length of the hypotenuse, 7.43, and the angle, bit of trig, tan theta will be 3.89 over 6.3296, and we get our angle. So I personally think a lot more efficient breaking it up into the two components, and a lot easier maths ends up at the end. Okay, so what sort of forces could we see? There's all sorts of different forces. We will see resistive forces. So whenever a body moves in a medium, air, water, whatever, then it will experience a subjective force. And that is always in the opposite direction to your motion. So resistance always opposes you. Resistance is usually proportional to the power of the velocity. If you think about it, imagine you're in a pool. The faster you move, the more resistance from the water you get. You'll usually find that the resistive force will be some constant times the velocity or some constant times the velocity squared, that sort of thing. Okay. Gravitational forces, also known as weight. That is, of course, mg. We'll see that a fair bit. Now, forces in pairs. That goes back to Newton's third law. If an object A exerts a force on object B, then B will also exert a force on A, but in the opposite direction. They balance. We have this thing called normal contact forces. So anytime an object is in contact with a surface, there's going to be a force on that object at right angles to the surface, and that is called the normal force, or the normal contact force. I guess the easiest way to explain it is, here I am standing, but obviously gravity is acting on me. So why am I not collapsing and falling down through the floor as gravity is pulling me down? Well, that's because the floor has also got a force being applied to me, and it's balancing out, hence I get to stand up. Frictional forces. So when we slide objects over surfaces, we'll get a frictional force. Now, it is a resistive force at the end of the day, so it again will be opposite the direction in which you're travelling. It usually is something like this, some multiple of the normal force. So you're on the surface, some normal force, friction is going to be some multiple of that normal force. Tension. That's to do with strings. Strings have tension. So if anything's attached to a string, then it'll have a tension force, but it'll be opposed to the object. So it'll go away from the object. When we're setting our problems up, it's usually easiest just to set positive to be the direction we're travelling. Okay, so whatever direction we're travelling, we say, well, that's the positive direction. Always draw a diagram so you can see the forces. It just makes the problems so much easier. We've got a heavy box, mass 32 kilos. It's got a handle on one side. Two people are going to try and move it across the floor. One pulls it horizontally on the handle with a force of 20 newtons. The other's pushing it from the other side of the box with a force of 25 newtons, but the box doesn't move. Draw a diagram of all the forces acting on the box. So here's a friend we'll get to know a lot. His name's Bob. Okay, there's Bob, representing the object. So what are all the forces acting on this object? Well, the first force I've got is that 20 Newton one, where the person's trying to pull it. We also have someone trying to push it, but they're in the same direction, so that'll be 25. There's this resistive force of friction. That's what's stopping it moving. If that wasn't there, well, then the object would have to move. So it has a resistive force. In this case, we're calling it friction. There also is these other forces. It still has the force due to gravity, but because it's sitting on a surface, it will have a normal contact force as well. So in fact, there's 5 forces there. We want to find the frictional force. So the ones I put in green there, the vertical ones, actually don't come into play in this question, Because friction's totally horizontal, I can just use the horizontal forces to come up with it. I am defining the resultant force to be going in the direction I would like the box to travel. I mean, the box is stationary, but that's the direction I'm trying to push it. The resultant force is not a force. So you don't put the resultant force on your force diagram. It's the result of all the forces. So mx double dot will equal, horizontally, we'll have F1, F2 minus F3 because it's going in the opposite direction. We know all the horizontal forces, the result of them all is 0 because the box is not moving. So there's no forces at all. Okay, sub in. 0 equals 20 plus 25 minus F3, which is the friction, and we have our frictional force. There it is, 45 newtons. We've got two trucks, a 30 kilo truck and a 50 kilo truck, and they're joined with a chain. Now, neglecting friction, so we're just going to assume friction doesn't come to play in this question. But we're going to pull the truck along with a force of 120 newtons. How much tension is in that chain? There are two different objects here, so I'm going to draw a force diagram for both objects. So if I just look at the truck on the left, there's good old Bob. On the left, I have a tension force going to the right. I'm not worrying about the vertical forces here, as they haven't in their diagram either, because this problem, again, can be totally solved using the horizontal forces. So mx double dot would equal tension. The resultant force on that truck is just T. They told me the mass was 30, so actually I can tidy that up a bit more. I'm just calling A for acceleration. So 30A will equal the tension. So I know the acceleration of this truck is the tension over 30. Now I'll go to the right truck. What's happening with that one? This one's got tension and it's going to the left. But those two values have to be equal because that chain is being pulled tight. So if the tensions weren't equal, then the chain would go slack or break or something like that. Then to the right we have this force of 120 newtons. So the resultant force, I've just changed the pronumeral, I made it y double dot, is equal to 120 minus t. Its mass is 50, but its acceleration is also A. It must have the same acceleration as the other truck. Because if it didn't, then that chain wouldn't be tight anymore. Because one would catch up to the other or something like that. Well, we worked out A was T on 30, so sub that in and play around with it, and we can work out the tension. And there it is, 45 newtons. Whoops. We have a mass of 2 kilograms. It's resting on a smooth plane, inclined at 30 degrees to the horizontal. It's connected to a mass of 4 kilograms by a light elastic string, which passes over a small pulley. Draw a diagram. Okay. Before I draw the force diagram, I'm going to draw an actual picture of what's happening there. So we've got this pulley sitting at the top of our plane, two masses attached to it. One's 2 kilograms, one's 4 kilograms. So what would be all the forces here? Okay, that 2 kilogram force is in contact with the plane, so there must be a normal force or contact force going off at right angles to the plane. So there's my first one. Force due to gravity. Mass is 2 here, so that'll be 2g. That'll be there. The 4 kilo one will also have a force due to gravity, so 4g. There will be tension going up the string. But so will that tension be there with the 4 kilo. But again, the string is tight, so those values must be the same. Now, you'll notice I didn't put friction in. They did say a smooth plane. It's a way of saying neglect friction. So normally if they don't mention friction, you usually neglect it. Find the tension in the string if the 4 kilo block is moving down. Okay, let's have a look at all the forces on that 4 kilogram block. We had 4g going down and we had tension going up. They were the only forces on that block. So the resultant force, so I've called it force R4, resultant on the 4 kilo block. It's moving down, so that's going to be my positive direction. So that'll be 4g minus t. So 4 times some acceleration will be 4g minus t. Okay, let's have a look at the 2 kilo block. Here's where I'm going to treat it a little bit differently. There's all the forces, but I actually have no idea what this normal force is, and I don't have any information in the problem that tells me what it is. Now, I could work it out, but I don't want to waste time. I don't have to work it out. Because all I'm really interested in is the tension, because that'll link me to the other problem. So instead of resolving horizontally and vertically, I resolve in the direction of the plane. Well, tension is totally along the plane, so it doesn't have any components I have to worry about. But the advantage of doing that, the normal force is at right angles to the plane. So it now doesn't come into play in my problem. It's exactly the same as those previous ones where we said, oh, it's totally horizontal, so I don't have to worry about the vertical forces. So by sort of rotating the problem, if you like, I could do the same thing here. I don't have to worry about the normal force. I'm just looking along the plane. But it does mean this vertical force of gravity, I have to resolve in components along the plane and at right angles to the plane. But using vectors, we could easily see which direction they go in. We have to work out where the angle will sit. 30 degrees will end up being there. Again, a bit of geometry will work that out for us. Okay, so I'm interested in the forces up the plane because it's tension that I'm interested in here. So I got tension going up the plane, but I would have 2g sine 30 because that's opposite the angle. The resultant force up the plane will equal T minus, because it's going in the opposite direction, 2g sine 30. But again, the whole thing's connected. So its acceleration must be the same as the other block's acceleration. So 2a will equal T minus 2g sine 30. Over on the left-hand side, playing around with that, it now means that 4g minus t will equal 2t minus 4g sine 30. Over on the right, we worked out 2a, so therefore 4a is 2t minus 4g sine 30. I now can get an expression for t. So playing around with that, make t the subject, and we can work all that out. Well, let's assume g is 9.8. They'll usually tell us whether to take it as 10 or take it as 9.8. So 19.6 newtons.